All right, let me see. Is that good enough? It's good enough for government work? Okay. So we're going to start with kind of an old problem that leads into, and I kind of made this point before. There was a problem we did that I said was chapter 8 before we got to chapter 8, roughly. So let's say I know that the standard deviation of some population is 1.29, and what else do I know the mean is 4.05, sure, and I take a sample of 32, sure. Can you tell me between what two data points we would find 95% of the data? In fact, maybe very carefully. Between what two sample means would we find 95% of all sample means? Oh, shit. So we've done this kind of problem before. If I could figure out the z-scores, I could figure out the sample means. I'm talking about sample means, right? So what two things have happened that tell me to do a certain procedure? That's so vague, I love it. I took a sample, and I'm talking about the, therefore, what must change? Standard deviation. So how exactly does the standard deviation change? Break out my new ones. I got some new ones. What's the formula for that? Yeah. So it's the old one. What I call the old standard deviations. The standard deviation for individuals, green, divided by the square root of n. Because this one that they gave me works for individuals. I've got sample, oh shit. I need the one that works for samples. It's that simple, that's it. I can't use that one, I gotta make the one that I can use. So it's gonna be 1.29 divided by?
Square root of 32.
And whatever the hell that is. Oh, I got calculators and they borrow one. What do you guys get? 0.228? Jugular. Yeah. All right, let me stop for a second. Okay. So pretty cool with that. That's kind of awesome. Those two things together act as a trigger to tell you when to do that thing. Standard deviation, I want to use the one that works for groups, for samples of size 32. I got to create it. I've got it. Now, I want to find 95% of all sample means. So inherent in this question, really, I would ask it better like I did on the test. The middle 95%. Yeah, so we know how to do that, hopefully. Most of us do. What's it look like then? How do I know this looks like this?
It's over 30.
Good, sample size over 30. Central limit theorem says, feel free, go ahead. It's normal enough. So I want to capture the middle 95%. So what would that look like? You doing the air? Dude, all right. I feel like it just kicked the winning field goal. That's awesome. Go to the ref. Yes. We've done this before. We've done actually this exact one before. How do I figure out what those two z-scores are? The chart, I really want you, what's the chart? It's the only area the chart understands. Area below is z-score, right? So it's not going to understand 0.95 or shit. But it will understand this, and what's that, of course? Yes. If it's 5% outside, there must be 2.5% on that side. Why did I cut in half? Because the picture is symmetric. Kick ass. So if you look up 0.025 in the z-score chart, the body, because it's an area, what do you find for the z-score?
1.96.
Yeah, which is close to 2, which is where the idea of unusual was built. So that's negative 1.96, right? And that's going to be, because again, it's symmetric. Yeah, I like it. So I know I want to catch 95%, which we're going to go from an area, I can go to a z-score, because I know it's normal, so I can use the chart. All right, that's the first step, really, is to realize I can find the z-scores that relate to the answers. How do I make these z-scores into raw scores, into actual data values? What formula do I use?
X equals your mean plus your z-score times your standard deviation.
Yeah, and the only thing that's going to be different here really is what's going to happen right there.
It's going to be your sample standard deviation.
So really what I'm capturing is sample means. Let me stop for a second. Same formulas, exactly the same formula. Anytime I have standard deviation in a formula, I just have to put the correct one in there. So it looks like all these formulas are different when really it's just putting the right standard deviation in there. Should it be S? Should it be sigma sub x bar? The formula itself didn't really change. What did it used to be? It used to be this. I mean, I'm not going to say that's different at all. Shit. I'm just using the right spread. And I'm talking about sample means. Oh, okay, same formula. And I could do one extra little thing here. Let's see if you guys are cool with this. I can actually write that as just plus or minus. Is that cool? Right? Yes, maybe? Okay. Somebody write this in its full glory then. Mu plus or minus z sigma over square root of n. I know we already did that work. We're going to put the that, but just to write it fully out. So pretty cool with that. That wasn't that much of a tweak. We started with this well-known equation. We're using samples, so I had to replace some stuff. And then I just put the plus or minus. Where's that coming from? Why? Plus or minus? Yeah, because anytime I want to find the middle whatever, it's going to be the same numbers. Just one's going to go up and one's going to go down. Yeah, I like it. So now if I put all the stuff in that I know, the mean was 4.05, give or take, 1.96. And we already did this work. Where'd it go? There, right in front of your face. Just plug this stuff in, right? So this is pretty much exactly that last problem in the handout we did yesterday, if I remember correctly. And then, whatever that is, 0.4, so it's going to be like, what are the two values you get?
4.49688. You want me to round it? And 3.6.
I like it. Do you see how that makes an interval? From this to this, what does that interval do? Catches 95% of the data. It's okay if you don't use the word catch, because that sounds kind of weird. All right. It catches 95% of all sample means would fall between that and that. That's what we mean by that when I take a sample, the mean should be close to the actual average. Do you see how this kind of further defines close? What does close mean? Well, this gives me an idea of what close means. Okay, all right, I like this. You're all very neutral at the moment. Go on, okay. So, this is a transitional step, because what we're actually going to do in chapter 8, when I'm about to do a study. So let me give you a nice example. I always love that little magic I can do. Let's say that all right, let's go back to Aaron Brockovich. So there's a known standard deviation of amounts of some pollutant in the water, right? There's just this. There's a known standard deviation of that. We go to an area, and do we know the average? We have to calculate that, right? So if I want to go to a certain town and I want to just test to see what it looks like their situation is in terms of pollutants in the water, I could take a sample of water. So actually it would be several samples, but a sample of the water situation in the town. And then calculate an average, right? Goes with me? So there's like, I'm going to take all this here away. Bye. Leave that over there. Stay. Okay. So we go to a town, we take a sample. And I told you that we happen to know the standard deviation, the regular standard deviation for the whole population. All towns have a certain standard deviation. And we're curious about this one town to see how it kind of fares. So if I look at what we just did, part of this I don't know, which we're getting closer to real statistics, because what part of this do I not know? So, if I took a sample, I definitely know the sample size, so that's known. So, what's the, and this part would be based on how confident I want to be, and why does it make sense to call this confidence? How confident would you be that there's a certain value in here? Well, what percentage did we say this catches? 95%. So how confident would you be there's a certain value in here? 95% confident, right? If you throw, I don't like fish, but I like this analogy. You throw a fishing net out, you catch 95% of all the fish in this lake, right? You just pissed off everybody who just came there for fishing, and you want to get a certain fish. How confident are you that you caught that certain fish? 95% confident. What's the chances you didn't catch that fish? 5%, because you left 5% of it behind for everybody else to scramble over, right? Okay, maybe. So far, a little bit. So, I have to replace this. I don't know. What's the best guess for mu in this situation? What's my best guess for mu, for the population of this town? What's my best guess? X bar. That's my best guess, right? Isn't the sample mean I take? If you take a sample and you find a sample mean, and you don't know what the actual mean is, what's your best guess for the actual mean? The sample mean you just took, right? Especially if you did a good random sample. So here's the official formula then. I really want you to get this. Does that make sense what I just said? If you have no idea about the average hop length of a certain frog, right? Do you know the hop lengths of frogs? I want somebody to go, yeah, that's my field study. I would go out, well, how would you figure it out? How would you start to figure it out? What would you do? Get some frogs, it's crazy. So you take a sample of frogs, and then you let them hop, or maybe you have some experiments where you have different things that make them hop, and then you take an average, right? So so if you get an average hop length of, well, I don't even know what makes sense, 1.5 inches. How's that sound? Sure. This is a really tiny frog. Right? What's your best guess for the actual, did you just figure out the actual average hop length for all frogs? All of these kind of frogs? No. But what's your best guess for that? 1.5. How good of a guess is that? What would affect that? How good of a guess is that? Size of the sample would affect it? Anyway, so standard deviation could also kind of tell me if my standard deviation is huge, I'm going to have a little less confidence in this, right? Unless it's kind of the wrong way to say it, but we'll get past that. So, is everybody cool with that by itself? If I take a sample and I get a sample mean, that is my current best guess for what the actual mean is. What these try to do is it takes that guess and it improves on it. It gives a range. It kind of communicates to people, where do I think the real mean is? It kind of communicates to people how certain I am about what I saw. Right? If one person's interval is 3.6 to 4.5 and somebody else's is 2 up to 7, who looks like they are more confident in what they see? Who looks like they are more sure about what they found? So these guys think it could be anywhere from 3.6 to 4.5. These guys think it could be from 2 to 7. Who is more sure about what they found? First one or the second one? First one, why? So yeah, if you're like, how many people are going to come tomorrow? 80 to 90, 80 to 90. You know, I can work with that. If you're like, how many people are going to come in? Anywhere from 10 to 150? Screw you, what the shit's that? Right? Improve your estimate. But see, that's a very quick way to communicate. If I had two people that had the exact same average, but one of them were like anywhere from 20 to 80, that's an average of 50. There you go, Jeff. And the other guy's like 0 to 100, right? Well, the 20 to 80 one I can work with a little bit better. It communicates beyond just the average that I get. It communicates kind of how certain that average is. It improves on our guess a little bit. Confidence intervals are very easily misused, and the language I use about them sometimes contributes to that, and I'm sorry, but it's just the way it kind of is. But we're going to try to point those out as we hit them. So here's what the formula looks like to create a confidence interval. For the population mean. So what I'm trying to do is I'm trying to capture the actual mean. So let's talk about this. There's the formula. Bam! So in a given problem, they have to give you a way to get this at least. They have to give you this, they have to give you this, and how do you figure out this? How did we figure out 1.96 over there? Where did that come from? The chart, but I had to tell you what number. Yeah, how confident we wanted to be. So the z-score will come from the confidence level. In fact, do you guys see, can I borrow your April? You guys see down here, see on the positive z-score side, in the bottom, what is that? Right-hand corner? I call it the baby chart. You guys see that? Look at 95% confidence level. What z-score is there? Holy shit. All right. Right? Now, you know Jeff's going to ask you to make a 97% confidence interval. It's not in the little baby chart, so you have to remember how to do the 97, 3%, 1.5%, look it up. But the little baby chart kicks ass because it's the most commonly used confidence levels. 95% is actually the most commonly used, which is why unusual was 2 standard deviations, because it relates to the most commonly used confidence interval, 95%. Can we stop for a second? I love you guys. Okay. I know. I'm doing a lot of concept right now. Hey, concrete formula, thank God. I'm going to do a little more concept, yes.
One thing I'm missing is, if this formula is an attempt to make a better estimate of the population mean, but the formula relies on the population standard deviation, what I'm not clear about is under what circumstances would you have the population standard deviation, but not the population.
You ready? Okay, I love it. Section 8.2 is going to be the absolute most honest section, and that's not the right way to say it, to be honest. Section 8.2 is where we don't know shit going into a situation, which is true a lot of the time. But in some cases, we do know let me see if I can really get this. What did that little mu stand for? It stood for the average of the town, right? And I don't have time to sample every particle of water. So I took a sample of water to estimate the town's average. So let's say the United States average is 7.2, as I write it through, 7.3 parts per million of whatever this thing is. And the town, we get a confidence. Everybody with me so far? So the whole United States, we know the average, 7.3, and we know the standard deviation is whatever of the population. Is that town a part of that population? If I take a town from the U.S., is it a part of the population of the U.S.? Yes. So what's its standard deviation? That one, I know it. If I take a sample from a population and I know the population standard deviation, I can use that. If I don't know this, what would I have to use? S. Because then I can calculate S from the sample I took. Right? Maybe. Good question. Let me see, I didn't really fully address it yet. What am I missing? Oh, so let's say we get, for the town, we get 9 to 11 is our confidence interval. Is that evidence that the town has elevated parts of this particulate in its water supply, whatever this pollutant is? Tell me, what do you think? Would that be evidence that the town has more than the United States average? Yes! Right? Because the whole interval is above this. So I'm 95% sure that the actual average for the town is caught by this interval. That is evidence, not proof. That is evidence that the town is above that. Yes?
Was there 2.5, if that's a 95% confidence interval, is there 2.5% chance that it's wrong?
Yes, because in this case it's a directional test that I'm using. I like it. So there's a 2.5% chance that I'm wrong when I say the town has an elevated. 2.5% chance you're wrong. Is that generally good for us humans? Oh, shit, yeah, I'm going to go with that. I'm going to say it looks like there's something wrong with the town. Then we go in and we do more in-depth analysis. So this would be just a normal water collection sampling. And then if we see an issue like this, then we go deep. Maybe. And then maybe it turns out that, there really isn't a problem. We just happen to sample bad parts. And actually, overall, it's not bad. Is that, you guys, semi with me? I know right now you're like, what the shit am I going to have to do? Just wait. We're still doing concept. We're going to do an actual hard problem in a minute. Okay, maybe. So is everybody semi with where this formula came from? I want you to remember this formula, let me write it again, came from this one. We know this one. I don't know mu, let me use x bar. I can't use sigma because I had to get x bar from a sample, I gotta change that. And the plus or minus is because I want to go up and down. They are the same form. Oh, there went my, what is that, 8th puberty? I think that's my 8th puberty. All right. Now, all right, here's the last piece. I think I ended up addressing your complete question. Okay. So here's the last part of this, and then we'll do an actual problem, dear God. I'm going to take away this. So I have a population. It has a mean, right? If I have a population and I want to know the mean something, there's a mean that exists for the population. Does everybody agree with me? Even if you don't, I don't care because it's true. All right. If I make a 95% confidence interval, what does that really mean? In fact, like, for example, if you flip a coin, what's the chances you get ahead? 50%. What the shit does that mean? I love my little brother. He's like, it's going to be, what the hell does 50% mean? It's going to be one of them. You can't flip it and see like, oh, it's heads and tails. No, it's not a Schrodinger's penny. No. So what does that mean? Probabilities don't mean anything until I do something a lot. If I flip it 10,000 times, I should get about 5,000 heads. That's what 50% means. On a single flip, it doesn't mean anything, which is why quantum mechanics is so weird, but let's not get into that. Okay. So, if I take a sample, you're stretching. If I take a sample from this population, Do you think that the x bar would equal to mu? Would the sample mean equal to, could it? Yes. Would you put money on them being equal? No. So let's say our x bar happens to land right there, right? You guys semi with me here so far. So there's an actual average age of gross month students. If I take a sample of 200 gross month students, I'll bet you anything that our sample mean will not equal the actual mean. Could it? Yeah. Could you flip a coin and get 100 heads in a row? Yeah, it's about the same. When I make my confidence interval, maybe it does this, right? So the correct way to interpret a confidence interval, somebody else could come along. Let's say blue team comes along. I should have made this red, but too bad. Blue team comes along and they get a mean there, and they make a confidence interval. Did they catch the real mean in their interval? No. So what the shit does this mean? This means if a ton of different groups make their own confidence intervals for some given population, 95% of those intervals will actually catch the real mean. 5% won't. That's what that means. Same way that 50% chance of heads doesn't mean shit for a single coin toss. Doesn't make any sense. For a single toss of a coin, it doesn't make any sense. Maybe. All right. So let's do a real problem, finally. See how all this shit kind of comes together into what you need to worry about. All right, let me put my little formula up here. Formula, baby. Get on there, Jeff. Let's try it again. All right, so let's say that I'm given, we take a sample of 87 items and find, I'm so creative today. The whole frog jumping thing just took it all out of me, it's gone. So we take a sample of 87 things and find an average of 492.8. We happen to know that the population standard deviation is, what do you got, Jeff? 28.7. Right, nothing major so far. We took a sample, we found a sample mean. We happen to know the population standard deviation, which I already addressed, is a very valid situation. Create the 98% confidence interval for the population mean, what I call the true mean. So I don't know the population mean at all. I took a sample, found a sample mean, right? I feel really good about the sample mean if my 87 was a really good random sample. But I need to communicate to somebody else kind of like how sure I am about what I see. Confidence interval is the first level of doing that. So what parts of the equation do we know? What's the only thing we don't know? Let me say it like that. We know the confidence interval. What part of the equation do I not know? Did I not give you? Z. But I gave you a way to find it, right? How do you find it? Can you draw what this would look like? 98%. How do I know what the picture looks like, by the way? Is this normal? Did it say it was normal? Okay, good. I didn't say it was normal, so I need the sample size. If I said it was normal, what does the sample size have to be? Anything it wants to be. 1 at least, it'd be weird to have a sample of 0. I don't know what you do. You guys, so if I don't say it's normal, n must be greater than 30 for the sample means to be normal. If I do say it's normal to start with, who gives a shit how big of a sample? In fact, chapter 6, we didn't take samples at all. We took one thing at a time. We were fine with it. Because I said it was normal. So n being greater than 30 saves your ass if I don't say it's normal to start with. That's the right way to look at that. So is it normal? Check, and greater than 30. How do you figure out the z-score? What would the picture look like? Well, now we know it looks like this. 98% confidence interval would look like field goal, right? Is this on your little baby chart? I don't think so. Ah, too bad. It's going to be in the other chart I give you today. So take a minute and see if you can figure out the z-scores for that. Who's got that? Anybody? Because what would be out here? Careful. What's up? I want to hear no -1. It's not -1 something. What is it? 2.33. You guys see that? Make sure you can find that. I'll wait for a second. Make sure you can find -233 for this. Let me know if you need help. I don't see anybody saying anything, so if that's -233, this of course is. So really, to be honest, I'm never gonna worry about this negative. Why do I not really worry about the negative? Because it is built in. It's built in. All I care about is the actual number, 2.33. That's how far out I gotta go. Stop for a minute. Yes?
Could we have used 3.5 if we looked at the other side?
You have to use what, sorry?
3.5 as the z-score?
Hell no, definitely. It's gotta be symmetric. So what areas below this one would be 0.98 plus 0.01 is 0.99. So if you look up 0.99, you should get positive 2.33. Not 0.9999, just 0.99.
Oh, okay.
Yeah. Okay. So now I know everything I need, right? You know, it's good for you, Jeff. Do I know everything I need? I know this, I know this, I know this, I know this. So how do I build this equation? What's x bar? 492.8, give or take this many steps. 28.7 divided by the square root of what? 87. Yes, no, maybe so.